Hello. This is Concrete Path. Today's lecture is that the final method of deflection of beams, that is the conjugate beam method. That conjugate beam method. So this is the best method of all of these methods. Subse best, we call it as Virat Kohli method also. Virat Kohli method. If no method acts anywhere, if no method is safe anywhere, we can say let's go and check conjugate beam method. But it's a conventional method also. But we can say sometimes it takes a lot of calculations to get to the deflection value or slope value. So, or we can also call it as surgical strike method. That if you want to get particular theta or delta, we only need to get some value, but at only that particular location. Theta at ith location and delta at ith location, you only need shear force at ith location and moment at ith location. Then we can get that. So what's actually a conjugate beam? So conjugate beam एक ऐसी बीम है जो आपका रियल बीम था, हम उसको रियल बीम कहेंगे, जो आपका क्वेश्चन में था, दैट्स रियल बीम. वैसे कॉन्जुगेट बीम एक ऐसी बीम है जिसमें जिसका लोडिंग लोडिंग डायग्राम, जिसकी लोडिंग डायग्राम आपका जो रियल बीम था उसका m/a डायग्राम है. सो जो आपकी रियल बीम है उसका आपने m/a डायग्राम बनाया. So we make that same m/a diagram loading diagram as a loading for this conjugate beam. So let's say you have आपका real beam था कुछ, this is your real beam and you have some sort of loading. Then we say that this was real beam. You want to make conjugate beam. So conjugate beam would be some sort of beam whose loading would be the bending moment m/a diagram of this loading, that real beam. Says there is some m/a diagram. This is m/a diagram of real beam. So we would make same loading diagram. We would make same m/a diagram as the loading diagram for that conjugate beam. So this is the loading diagram for your conjugate beam. So if you go now on the concept is that conjugate beam की loading diagram is the m/a diagram of real beam. So the setups are like that. Get the m/a diagram of real beam. So जो आपका क्वेश्चन है वहां से आपने बेंडिंग मोमेंट डायग्राम बनाई, then you divide by EI. So we got the m/a diagram of real beam. Then make that as a loading diagram of conjugate beam. Then you calculate shear forces and bending moments of conjugate beam, and you can get the delta and theta. Let's say how we are going for that. Let's say we know that. So this is your conjugate beam and this is your real beam. We say that जो आपका conjugate beam का loading है, that the loading diagram of conjugate beam that equals to m/a diagram of say in the real beam. So if we say we know that w dx integral that equals to shear force also. Can we say that that's equals to shear force also? Let's say you calculate about 2 points on the beam, say such that one was at point 0, next one was at point just extending to point 0.00000. So then we can say limit was from x from 0 to point A. This was your point A. So we can say VA minus 0. We can say shear force at VA. We can directly say shear force at any point A. So we can write directly that integral W dx equals to shear force. We know that dV by dx equals to shear force, that loading intensity. So we can say V equals to W dx. तो आपका जो shear force conjugate beam का है, that equals to M by EI diagram of that M by EI diagram of real beam. But if we know that result, that curvature of beam that equals to d2y by dx2, that equals to d theta by dx, that equals to M by EI. Do you know that? So if we say what's the value of d theta, that's M by EI into dx. So we can substitute that value here. We can say this value comes out to be equals to d theta. So we say that what's the value of integral d theta? So we can say shear force in the conjugate beam equals to theta in the real beam. So if you want to say what's the question was like, you had a beam, get the theta at any point, slope bata do kisi point ka. We would say let's make conjugate beam whose loading diagram is equals to M by EI diagram of your real beam. Then you calculate the shear force at that particular location only. If you only know that shear force at that particular location, just you can get the theta b. You don't need to get the all that deflection profile. You just need to get the shear force at that particular location. So this method is best if you want to know that particular theta at any support. Let's say you want to find theta at this support. So this method is very useful because you only need the shear force here. What's the shear force or reaction developed at the support? That's very useful here. So it's very useful if you need to get that theta at any particular support, because if you get the reaction here at the support, that's very easy because you know that summation Fy goes to 0. So from we call it as theorem 1 also, that shear force, you write shear force in the in conjugate beam equals to slope in the real beam. So you need to get, actually question was that you get the theta at any particular location in the real beam. So for that, if we get the shear force in the conjugate beam, that's already equals to theta in the real beam. Similarly, we know from this result we can also derive one more thing. We have that finally we got that V equals to theta. We got it. So if we again integrate it, let's say we were having V, then you'd say V dx, and your here it was theta, integral theta dx. So if you integrate it one more time, from this step, if you go reach up to this point, from this side this is conjugate beam, for this side this is real beam. So we know that dm by dx equals to shear force. So we can say m equals to v dx, or dm equals to v dx. So total moment equals to integral v dx. So we can say m equals to v into some length L. So finally we got this integral v dx equals to some moment m. So we can say this is moment m, and we know that dy by dx equals to theta. So we can say dy equals to theta dx, and if we integral it, so we can say this y equals to this. So we can say moment developed in the conjugate beam at any particular location, that's equals to deflection in the real beam at that particular location. So this one is your theorem 2 in the conjugate beam method. Theorem 2, that deflection, that moment, if you want to find deflection at any point B, I would say deflection in the real beam equals to moment in the conjugate beam at that particular location. So we need to, so let's remember that delta is m and theta is shear force. So just we need these 2 points now. Now let's analyze what's happening inside. Say you are making from real beam, to some another beam. Say you are having this was your real beam. You are making conjugate beam, but how can you make this conjugate beam possible? Let's say you are making you are saying that let's say because of some loading, there was some loading on the general beam, then because of that there would be some deflection and some slope. Let's say the slope was theta and deflection was delta. So at that point B, so same point would be here B. So आप बोल रहे हो कि जो आपका delta in the real beam है, that's moment developed in the conjugate beam. See, it was free end. So यहाँ पे obviously ये हम कह सकते हैं कि delta would be there. We can say delta would be there because it is a real beam. There is a free end. So we can say there is some deflection. But how can it be moment developed in the conjugate beam? How it's possible that here is some moment? How it's possible? How it's possible that there is some moment? Let's say there is some moment M, moment in the conjugate beam at that particular location, only. Similarly, let's say that we got theta here also. We say that if at the free end there is some theta, okay, there's no problem with that. But how the shear force is there in the conjugate beam? That means there should be shear force in the conjugate beam also at that particular location. Let's say there's some shear force also. That means whenever there is some shear force and there is some moment also, we can say that's the character of that is the character of fixed support. Can we say that that's the character of fixed support? So your free end has changed to a fixed end to ensure this transition. So we call it as changing the supports. Yeah, we call it as changing the support conditions. To make this transition possible, we call to the changing the supports. So we say that your free end has become fixed end. Can we say that? Similarly, say we know that in the fixed beam, यहाँ पे आपका theta 0 था और deflection भी 0 था. That means if you want to analyze it now in the conjugate beam, that means shear force अगर आपका 0 होता conjugate beam में, that means आपका deflection 0 होता real beam में. Similarly आपका अगर आपका moment 0 होता conjugate beam में, that means आपका deflection होता 0 real beam में. Similarly अगर आपका shear force 0 होता conjugate beam में, आपका theta होगा 0 in the real beam. So if you want to make this possible, that means here the shear force should be 0, moment should be 0. That's only possible if the support is if this point is free. So your fixed end has changed to free end and vice versa. This is vice versa. Understand? So if you now we have to say what are the different possibilities of the supports and how can they be transformed into conjugate beam. Say let's take through a few examples. Say this was let's take this then this one, that this was your hinge support. यहाँ पे आपका there is theta is not 0, but यहाँ पे delta आपका 0 होता है. It does not allow deflection at that support. This was your real beam. To make a conjugate beam, we say at this point there should be some see, delta means moment. So moment here should be 0, but shear force should not be 0. That's possible. Say if you want to make a roller or a hinge itself, there are two possibilities for hinge support changing into conjugate beam support. So there is either we can say roller support, or we can say either or hinge itself. There is no hard and fast rule for that. You can select any of these two. Similarly, अगर आपका roller support होता, roller support यहाँ पे same basis पे हम बोलेंगे कि theta आपका 0 नहीं होता है, but यहाँ पे deflection 0 होता है. Similarly, we can say moment यहाँ पे 0 होता है, then shear force is not 0 here. So to make this possible happen, to make this thing happen, we can say there should be some support which can give some reaction such that shear force is not 0, and there should be some support which would not provide any moment. So आपका roller ही रहेगा, या आपका roller hinge में change हो सकता है. It's up to you which one you can select. Next one I want to say let's have internal roller. That means यहाँ से भी continuous है और यहाँ से भी beam continuous है, but you have internal roller, internal roller. So internal roller पे क्या होता है कि यहाँ पे आपका डेल्टा is 0, but theta is not 0. But the difference between the two, we can say, difference comes here, that if you want to make same support here, let's say what would happen here the theta is, we can say, we have to make if the delta is 0, that means moment here is 0. If the theta is 0, that means theta is not 0, that means shear force is not 0. You can say shear force is not 0. Yeah, but the thing is, moment should not be 0. Let's say this is continuous. Let's take example for this one to understand this problem. Let's take it as a case A. Say for the case A, let's say loading is somewhat in this fashion. Can you tell that moment at hinge is 0? Yeah, moment at roller is 0. Can you tell? Based on the loading, can you tell the moment is 0 here? This one is your internal roller. We call it, इसको हम बोलेंगे internal roller. Similarly, this one is internal roller. So इसको चेंज करने के लिए हमें ऐसा सपोर्ट डालना है, यहाँ पे ऐसी कंडीशन क्रिएट करनी है such that if the delta is 0 here, moment should be 0. But for this case, want to say if there is an overhang or the beam is continuous and this is internal roller, that means there is some moment developed. There is a chance of moment developed in the support. And that say, I want from you what's the moment developed at this hinge, this roller. Is this 0? Or is there any moment developed? So we can say from the free body diagram that moment developed at this roller equals to WL square by 2. So there is some moment, but it is a roller support. But because of the overhang, we have moment developed at this support. I hope you can relate the thing. That means now to ensure that there should be the moment of 0 at this support, because if the delta is 0, that means moment should be 0 in the conjugate beam. That's only possible if you make it as an internal hinge. So your internal roller changes to internal hinge. Final conclusion that internal roller changes to internal hinge. Similarly, if there was internal pin, let's say this was internal pin, this will also change to internal hinge, because your delta was 0 here, that means moment should be 0 here, but shear force we can transfer from internal hinge. Okay, this is the main conclusion of that internal roller. Difference between roller and internal roller is that in the roller support, there is no moment transfer. There won't be any moment directly, you can say. But if the roller is internal, between some spans, there is possibility that moment will be at that point, at that roller support. So to make this possible, that delta should be 0, we have to make sure that moment should be 0. That's possible if you make that as an internal hinge. Let's have guided roller now. Guided roller. We have guided roller. How can you make this support in the this was your real beam? How can you make this support in the this conjugate beam? See, we have to say what's the condition that theta and delta here. We say it can allow delta. Delta ये allow करेगा. That means delta आपका 0 नहीं होना चाहिए. That means there should be some moment, there should be some support there where the moment is not 0 in the conjugate beam, and theta is not 0. Theta is 0 here because there is some moment developed in the that guided roller that makes this theta 0. We have solved one problem on that also, that theta is 0 in the guided roller at that point. So we can say shear force is 0. What is the condition for this? How can you make this support that's having some moment but shear force is not 0? We can say that's itself the guided roller. वो खुद ही guided roller है, because it won't allow any shear force, because यहाँ पे del if it allows if it allows delta, that means it does not give any reaction, it does not give any reaction shear force. So you can say shear force is 0, but it can allow moment, it would allow a moment of m that is not 0. So guided roller changes to guided roller itself. Now one problem arises that, let's say you are having a fixed beam. So यहाँ पे we know that delta is 0, theta is 0, delta is 0, theta is 0. This is real beam. To make conjugate beam, we say that moment should be 0, shear should be 0, moment should be 0, shear should be 0. But how it's possible? Beam तो रहेगी नहीं है. No support is there. Where is the beam going to land? It's going to land on your head, obviously. So how can you say beam is stable now? We say that we are just solving the question. To make the things clear, we say let's apply a pseudo support here. Let's apply a pseudo support here such that reaction A and reaction B, we say that reaction A equals to B equals to 0. Reaction finally आप calculation करो जो आपका loading था because of the M/A diagram, जो आपका loading बना उससे आपने calculation किया that there are two supports, we call them as pseudo supports, as we have in the Castigliano's theorem, that those pseudo loads you are applying, then you set them to 0, set A and B equals to 0 after calculation. After your work is done, you say then let's say the reactions are 0. Similarly, you have cantilever, proper cantilever, that आपका यहाँ पे डेल्टा 0 है और शेयर दैट थीटा इज ऑल्सो 0, और यहाँ पे आपका रिएक्शन होता है, दैट मीन्स यहाँ पे थीटा इज नॉट 0 बट यहाँ पे आपका डेल्टा 0 होता है. टू मेक ए conjugate beam of this, we say at this point moment should be 0, shear force should be 0, that means it's a free end, and the roller support, at the roller support, that means theta is 0, theta is not 0, that means shear force is not 0 but moment is 0. So that's possible only if there is some roller or some internal hinge, we can say roller or internal hinge. But is this stable? Let's say you apply a load here, it would rotate, it would struck to your head if you are here. आप अगर यहाँ पे होते तो आपकी नाक पता ही है क्या होता है. तो to make this stable, we say let's apply again some fictitious pseudo load, pseudo reaction. This is your pseudo reaction, pseudo reaction again. Then to calculate some effect, we say let's set finally the value of the pseudo reaction equals to 0. Let's make the complex now. Let's make the diagram complex now. Let's say this one. This is your real beam. यहाँ पे internal hinge, यहाँ पे roller, और यहाँ पे point load. So we have to make that conjugate beam. So let's say this is the conjugate beam without supports. We would say यहाँ पे theta 0 है, delta भी 0 है. तो यहाँ पे आपका shear force at the internal hinge, यहाँ पे theta ये allow करता है, और वो भी दोनों साइड से, because theta right is not equals to theta right, theta left. And similarly we say that delta is not also 0 because it would deflect under the load, internal roller, internal hinge. Similarly you have internal roller here. See here we can say theta is not 0 and delta is 0. So now first condition is that moment equals to 0, shear equals to 0, that means fixed changes to free. After that you have theta not 0, that means shear force is not 0. Shear force is not 0 and moment is also not 0. That means internal hinge changes to internal roller. If the load is there, we can say internal roller पे कुछ moment होगा. So moment is not 0, internal roller. Then after that you have theta 0, theta not 0, that means shear force is not 0, but moment is 0. That means internal hinge. Shear force not 0, but moment 0. Internal hinge. Then after that you have point load. At the point load location, we say theta is not 0, delta is not 0. So there is some moment that fixed support. Moment not 0, shear force not 0. Yeah, I think this is sufficient now. This is and we would solve now problems now. We would take problems. Let's take problems now. चलो प्रॉब्लम स्टार्ट करते हैं बिना किसी रोक टोक के. let's say that this is hinge support and this is roller support. So a load is acting at the midspan. This is L by 2. This is L by 2. And we need to get delta at point T and theta at point K. So this point is point K. This point is point T. That is at L by 4. This is also at L by 4. So if you are saying that delta at T, that means you have to make conjugate beam, and you have to calculate at that point moment at T, and similarly you have to calculate shear force at point K. If you directly get these 2 points, you don't have to go for the all calculation of that full beam. You don't have to go full beam shear force diagram BMD. No, that's why it's called as surgical strike method. So you have one load, so we can say what are the reactions. Reaction is, say, the other reaction is P by 2. Similarly, reaction here is P by 2. So from the given real beam, we can make the BMD. We can make the BMD that at the midspan it would be PL by 4 EI. PL by 4 EI. So this is positive. Now to make the so first step was to make the M by EI diagram of the real beam. Then you set same M by EI diagram of the real beam as loading diagram of conjugate beam. So now we are making same M by EI diagram as the loading diagram of conjugate beam. So but we have to ensure that we have to change the supporters also. Say this is your internal, say this is your hinge support, so we can make hinge support also, or we can make roller support also. It's not a hard and fast rule. Say this is your internal hinge, and this one is your internal roller. Now if the BMD is positive, that means loading is upwards. You have to make the loading upwards in the conjugate beam. This is one statement, you have to write it there. If the BMD is upwards positive, that is loading, you have to make that loading upwards. Let's make the loading upwards. So loading is upwards. So we got the loading of PL by 4 EI uniformly varying in the length L by 2. So can we get the reactions now? If we get one reaction, then we can say what's the that at particular location we need to get theta K. That means we need to get the shear force at particular location K. At this point, we need to get the shear force. Firstly, we can say what's the reaction. Reaction would be downwards. Both the reaction would be downwards. So we can say one of the reaction would be area of this triangle, area of the one part of the triangle, that bigger triangle का जो एक छोटा triangle बन रहा है उसका area, that would be reaction 1. That's 1 by 2 PL by 4 EI, or length L by 2. That's PL square by 16 EI. if you say, do you know this result also? That's equals to theta at the support. That's equal to theta at A, actually, PL square by 16 EI. So if you want to find what is the theta here, we know that theta here would be shear force in the conjugate beam. We know that shear force here is the reaction also itself. That means theta A is PL square by 16 EI. Can we say that? Yeah. After that, you want to get what's the theta at K? Theta K. That means get the shear force at that point K. So if you want to get the shear force at that point K, let's have this triangular part, this load acting down upwards, and you have a reaction downwards, that PL square by 16 EI, and this is point K at L by 4. So we need to get the shear force at that particular location. Say the shear force here is upwards. Say the shear force here is VK. Okay, and loading is varying from 0 to PL by 4. So we can write here the value should be, by the similar triangles, that it should be PL by 4 EI, but only half of it, because you are going for length 1 by half of the length, and for the L by 2 we have PL by 4 EI, and we can write for 0.5 L you have PL by 4 EI, but you need for 0.25 L. So can we say that what is the total shear force at this point? Can you say what is the shear force at point K? That's PL square by 16 EI minus area of the triangle 1 by 2 L by 4 PL by 4 EI into 0.25 by 0.5, that means 1 by 2. So we get the value of that PL square by 8, 1632. 4 square by 2, 4 square by 4. That's 64. 16 minus 64. 16 was minus 64. P 1 by 2. This is 1 by 2. L by 4. PL by 4 EI for 0.5 length, but we need for 0.25 length. We need for this length, that's 1 by 2. So we can write 16 inverse minus that upward loading of PL square by 4 4s are 16. 16 into 2 2s are 4. 3 by 64. So we get a value of 3 by 64. 3 by 64 PL square by EI. That's the shear force at that particular location. So we can say, so this is in the conjugate beam. It is in the conjugate beam. We can say theta at point K in the real beam, that equals to 3 by 64 PL square by EI. Similarly, you need to get the value of delta at T. So delta at T means once you got the reaction, that means here the reaction is also same now, PL square by 16 EI. So we need to get the moment at this location. At this location, you need to get the value of moment. Now we need to get the value of moment at this location. So you have triangle. You have this triangle. Downward load of PL square by 16 EI is acting, and length is L by 4, and an upward load of that we have calculated earlier, that PL by 4 EI and into 1 by 2, that's PL by 8 EI. So let's say the moment developed here is some moment M, moment MK, MT, and there is some shear force. We don't care about the shear force here. We are worried about the moment T, MT. Let's calculate MT. So we can say summation of moments about T equals to 0. We can write clockwise PL square by 16 EI into length of L by 4. Then you have anti-clockwise moment of the area of that triangular. We can say 1 by 2 PL by 4 PL by 8 EI and length of L by 4, and it is acting at this location, that 1 by 3rd of L by 4. and you have moment t, that's clockwise, plus mt equals to 0. So we can write bending moment at any location t, that equals to difference of the two. So we can say this is 16 into 4 minus inverse that 1 by 64 minus 1 by 2 into 8 into 4 into 12. That's that's 11 by 768. 11 by 768, and you have PL square. Actually, this is L. It's not square. This is PL by 16 here. So we write PL. But the thing is, it should not be moment. Yeah, yeah. This is the deflection actually, nah. What is the value of at the mid? We got PL by 4. Yeah, PL by 4. PL by 4. PL square. PL square. Is everything okay? Yeah, this was the reaction actually. This was the reaction. Yeah, this is the reaction. PL, reaction into length L by 4. The reaction into length L by 4. Yeah, it should have unit of PL cube. PL cube there, because you need to get deflection. That's PL cube. So we're at 11 by 768. 11 by 768, and you keep a sign of minus, negative sign. Negative sign. That means delta at t is minus 1, that 11 by 768 PL cube by EI. PL cube by EI. This is the deflection at point T. Yeah, 11 by 768 PL cube by EI. Let's take problem 2. Second problem we can take. Let's say the beam is subjected to pure bending only. This is point A, this is point B, roller support, and a concentrated moment is acting in the 1/3 part of the beam, middle 1/3. Say this is A, this is A, this is A. So can you make the shear force diagram? This is shear force diagram. Why? Supports. You can do summation of moments also. The shear force diagram would look like a straight line without any curvature. You can say shear force is 0. Then after that we are left with bending moment diagram. Say this is our bending moment diagram of the real beam. We say up to this point there is no shear force, that means no bending moment. So then we have a clockwise moment acting here, that means a sudden rise of m. Then after that no moment is acting, that means constant. After that we have a anti-clockwise moment, that means sudden drop of BMD by m. It was upwards. So this is sagging bending moment, that's why it's upwards. So we have to show the loading upwards. So you divide by EI, that's your loading for conjugate beam. This was real beam, finally it became conjugate beam. So you can either make it in this fashion, or you can keep the supports as they were. So you made a conjugate beam now. You need to get the question was to get the delta maximum. We can say delta maximum would be at the mid. We can clearly say that loading is symmetric. We can say delta maximum would be at the mid. So for that we need to get the moment at the mid. So this is your delta max in the real beam. So we need to get moment mid in the conjugate beam. So let's draw from this diagram, loading diagram, shear force diagram, then after that bending moment diagram. So can you say that the reaction here would be downwards? Reaction here would be downwards. That equals to area of this part. This is length A by 2. You can say the reaction here would be M by EI. This is UDL into length A by 2. So this is the reaction. Then then after that there's no loading, so shear force remains constant, shear force diagram. Then after that loading is upwards. So finally we have already shown you that if the loading of the column is at length of x, then how that variation would be. So it would vary in this fashion. Here the reaction is also downwards. Reaction is downwards. That here it's also MA by 2 EI. So this is negative area, this is positive area. Can you draw the BMD now? Let's say area is negative and this is x to the power 0. That means it's a triangular variation, that negative, that's equals to area of the curve between the 2 points. That's MA, the length here is A, this length is A. We can write MA square by 2 EI up to this point. Then after that your shear force is linear variation. Shear force diagram is a linear variation of shear force is linear variation up to point A by 2. So we can say what should be the value of moment at mid. Get the value of moment at mid. We can say that equals to area between the 2 points. We're at M2 equals to M2 minus M1 equals to area of the SFD between the 2 points. This one 1 by 2, but the area is also negative, 1 by 2 MA by 2 EI, MA by 2 EI into length of A by 2. So moment 2 equals to, your moment 1 was actually minus, so moment 1 was minus MA square by 2 EI. When you transfer it, it would remain negative, because you have to say minus of this value. Finally it will become positive, again negative. So we can write M2 equals to this value minus this value, that area of the SFD between the 2 points, and you will get a value of minus 5 by 8 MA square by EI. This SFD BMD you have to do yourselves now. You should be able to solve the problems yourselves, that SFD BMD. Our main concern here is to get the delta at that location, at the mid location. So the variation would be a 2-degree variation. So this is our 2-degree variation. This part was 1 degree. So finally we got moment mid. We don't need to get this part. We say moment mid equals to 5 by 8 minus 5 by 8 WA square MA square by EI. That means your deflection maximum is delta maximum in the real beam. That equals to minus 5 by 8 MA square by EI. Let's take one more problem. Let's take one more. Let's say this is 4 kilonewton meter, this is 2 kilonewton meter, and you need to get theta A, theta B, delta C. Can you get the reactions? Say net value of net moment is acting in the clockwise direction, anti-clockwise direction, that equals to 4 minus 2, that's 2. Yeah, and you divide that 2 between the length, so the reaction would be M by L, and here it would be downwards M by L. So here the reaction would be 2 by 4, that's 0.5, and the reaction here would be downwards 0.5. So we need to get the theta A. For the theta A in the real beam, you need to get shear force at A in the conjugate beam. So firstly you need to get the M by EI diagram. of the real beam. Then after that we can say what should be the loading diagram. See, can you make that M by EI diagram for this beam? Say यहाँ पे आपका 2 kilonewton meter is acting clockwise, that means positive upwards rise of 2 kilonewton. So you divide by EI, that's your M by EI diagram. So that's 2 by EI. Then इस point पे आपका 4 by EI है. That means bending moment is 4 here. That means you can divide by EI. Then between the two there is no loading, so we can say this is linear variation between the two. पिछली क्लास में भी हमने ऐसे ही एक क्वेश्चन किया था. Let's say you got the loading, that's positive. That means for the conjugate beam, you are now making conjugate beam. उसके लिए आपके supports से, let's take the supports as it is, and the loading should be upwards or downwards. Loading should be, I think loading should be upwards. Loading should be upwards. So this is your loading for the conjugate beam. Now there would be some reaction downwards and there would be some reaction downwards, but you need to get the theta A. That means get the reaction get the reaction RA and get the reaction theta B के लिए आपको reaction RB find करनी है, and theta A के लिए reaction RA. That means this reaction is RA and this reaction is RB. Get these two values. We can get these two values. We can say total length is 4 meter. Now calculate the reactions. Let's calculate the reactions. What is the area of that triangle? Area of the whole. What's the area of the that trapezium? 1 by 2. Sum of parallel sides, that's 2 plus 4 by EI for a length of 4 meter. That is the total loading. That's reaction A plus reaction B. Similarly, let's take moments about point B. Let's take moments about point B. Summation of moments about point B equals to 0. Then we write reaction A anti-clockwise RA into 4 minus times. Then we have you have UDL of 2. So we can write positive UDL 2 by EI WL square by 2. Then we have triangular variation, that 1 by 2. Difference of the two, this value is 2 by EI. Area of the triangle 1 by 2 W into X, W into X, W into X, W into X. Acting at a length of, what is this value? This is 4 by 3. Yeah. And you get the value of reaction A. Once you got the reaction A, that's equals to, that's real reaction at A in the conjugate beam, that's equals to share that theta A in your conjugate beam. Yeah, in the real beam, that you need to calculate. You can check it by yourself. And similarly, once you got the reaction A, you can get the reaction B. That's from the relation that earlier we saw. This area of that curve, that's total loading area minus reaction A, and that equals to theta B in the real beam. So you can check, you can try it yourselves. And third one is that get the delta at C. Get the delta at C. So for the delta at C, you need to get the moment developed at C. So you can cut the section. You can cut the section at 2 meter from the support. So this is 2 meter. Here the loading was 2, and here it was 4. So that means at the mid it would be 3 by EI. So yeah, you have this loading upwards. Let's say moment developed here is M at C, and direction was downwards RA, and you can do summation of moments. Say this centroid is here, इसका centroid यहाँ पे है, इसकी length यहाँ पे, then you can calculate moment C in the conjugate beam. That's equals to delta at C in the real beam. Very easy, na? You can calculate it. This is a practice problem for you. Try it by yourself. Next one. Let's take next one. A load is acting at L by 4. This is load B. This is support A. This is roller. We can directly get BMD. That's 3. This is L by 4. This is 3L by 4. We can get 3PL by 16. Yeah, and you divide by EI. So this is your M by EI diagram. And this is positive. That means loading is upwards. So we can make conjugate beam. That's let's keep the supports as they were. So this is your support A, this is support B. There is some reaction RA, there is some reaction RB. Then the question is that says get the theta at the midspan and get the delta at the midspan. So you need to get the delta and theta at the mid. So for the delta mid in the real beam में आपको delta और थीटा फाइंड करना है रियल बीम में. उसके लिए आपको कॉन्जुगेट बीम में फॉर थीटा मिड यू नीड टू गेट shear force at the mid, and for the delta you need to get moment at the mid. Easy? Can you do it? Let's say the reaction here, we need reaction. One of the reaction we need. See, if you calculate reaction A, that would be that. So one of the reaction you need to calculate, that's for sure. If you get one reaction, then after that you can cut the section at mid. So I think which side is easy. Say this is L by 2, this is also L by 2. If you cut section at L by 2, and before that you need to get one of the reaction. Which reaction would you prefer solving? Say I think I should take reaction B here, because the loading here is it's a triangular variation, but in this part there is some triangle, then after that there some trapezium, so the calculation would become very difficult, lengthy calculations we can say. But for this part your calculation will become very easy at the midspan. So try to get reaction B. Try to get reaction B. So we can write reaction B equals to, we can write A plus B equals to area between the 2 points, and we don't care about that. We say what's the reaction B. We can write summation of moments about point A. Let's write summation of moments about point A equals to 0. Then we write B is acting downwards, so clockwise B into L. Then we have two triangles that, let's say loading is upwards, so centroid इसका centroid यहाँ पे है और इसका centroid यहाँ पे है, so we need to get the centroids also. BL acting upwards, so we can say it's acting upwards, that's my negative area of the triangle 1 by 2 3p L by 16 EI, and for a length of L by 4, and it is acting at 2 by 3rd of L by 2, 2 by 3rd of L by 4, 2 by 3rd of L by 4. Then we have one more that's anti-clockwise about point A, area of that triangle also. We can write 1 by 2 3p L by 16 EI into length of 3L by 4, and it is acting at, this length is it is L by 4, and it is also that this length is equals to 1 by 3rd of 3L by 4. So we can write L by 4 plus 1 by 3rd of 3L by 4. So we can get the reaction that equals to 0. We can get the reaction B. That comes out to be equals to 5 by 128 PL square by EI. So we got the reaction B. So if you got reaction B, if the question was get the slope format at this support, we can say slope format at this support B, that's equals to reaction B. This is real beam, this is conjugate beam. So we could have solved for the reaction B, that theta B. Now the main goal is to get the theta mid and delta mid. उसके लिए आपको यहाँ का जो ordinate है, can you get this ordinate from the BMD M by EI diagram? Can you get this ordinate? So we say 3PL by 16 is for length of 3L by 4, but we need for this is 3PL by 16 EI. This was for length of 3L by 4, but we need for only L by 2. Okay, now we can cut this section for the shear for the theta. We can say let's cut the section. We got a reaction of downwards 5 by 128 PL square by EI. So हमने reaction find की. So let's say यहाँ पे shear force कुछ होगा, that we need to get shear force at the mid. We can write shear force at the mid. And or let's say loading was also upwards. Loading is also upwards. We need to get we have calculated the loading at that point L by 2 3PL by 16 EI. Okay, right. The loading UVL is equals to 3PL by 16 EI, and it was for length of 0.75 L, that is 3 by 4 of L, but we need for L by 2. And now this length is L by 2. Let's say we need actually we need theta maximum. Yeah, we need हमें find करना है theta mid or delta mid. That means we need to get shear force at the mid, and we need to get moment at the mid. So let's say there is also moment developed here, some moment M mid. So let's apply summation of Fy equals to 0. We can write summation of Fy goes to 0. That means shear force of Vm upwards, then area of that triangle 1 by 2, 3 by 16, 0.5 by 0.75. That we have PL square by EI. Then we have downwards. Minus 5 by 128 PL square by EI. So we can get the shear force at the mid. Shear force at the mid. Can you calculate that shear force at the mid? That equals to 1 by 128 PL square by EI. So that means your delta at the mid is equals to this value. So we got the deflection at the mid. Actually it should be no, this is not correct. Actually this should be cube. The calculation is for slope. This was the slope equation calculation. So delta, we need to get the shear force. That should be in the form of L cube. It should be in the form of L cube. Yeah, sorry, theta. It's not delta, it is theta. It's theta, because from shear force we get theta, not delta. Not delta, yeah. थीटा का ये जो यूनिट होता है that's PL square, and delta का यूनिट होता है PL cube. So we have to also check by that. Say shear force we need to get at the midspan. You can calculate the value here, and the shear force at the mid comes out to be equals to shear force at the mid PL square by 32. That's PL square by 32 EI. So same value would be theta at the midspan, PL square by 32 EI. Now we need to get the moment at the mid. Moment at the mid in the conjugate beam, that is equals to delta at the mid in the real beam by the theorem 2. So let's apply summation of moments about point M equals to 0. We can write moment M is acting anti-clockwise, that is positive M at M. Then we write negative 5 by 128 clockwise. So we write positive 5 by 128 PL square by EI. Then we have negative area of that triangle 1 by 2, 3 PL by 16. Then we have 0.5 by 0.75. Then we have PL square by EI. Then it is acting at the centroid. Centroid कहाँ पे act कर रहा है इसका? So centroid is acting for a length of 1/3 of L by 2. That's L by 6. and that's your moment equals to 0. So moment at mid comes out to be equals to yeah. Actually the calculation for that theta actually calculation ये आ रहा था. पहली calculation is not correct. So you have to that you have to write that theta at the mid comes out to be equals to इनका calculation आप करोगे इन दोनों का तो आपका वैल्यू जो आएगा वो that's 1/128 PL square by EI theta at the mid. Then we have delta at the mid. Delta at the mid. Delta at the mid. That equals to minus 11 by 768. So minus 11 by 768 PLQ by EI. That's also get a delta at the mid in the real beam. Moment at the mid in the conjugate beam. So we can write this one. Downward means deflection is downwards. So this is downward deflection. Okay, let's have one more. Let's have one more problem. Let's take one more problem that let's say this one. 12, 12, 15, 12, 12, 15, 12, 12, 15. This is 12. There is a load of यहाँ पे लोड है 8 किलो न्यूटन. उसके बाद after 12 meter there is internal hinge. Then after that there is a support. Then there is a moment developed, moment applied 30 kilonewton meter. Say this is point A, point B, point C, point D. हमें find करना है theta at C from both the sides, because at the internal hinge theta is different on both the sides. If the loading is not symmetric, that means theta would be different in the both sides of that internal hinge. So we need to get theta BC, theta CA, and we need to get theta CD. Also we need to get delta at point internal hinge, delta C. So we need to get actually we need to get what in the conjugate beam? We need to get shear force just to the left of C and shear force just to the right of C. And we need to get moment at particular location C. In it's not in the real beam, it should be in the conjugate beam. You can tell moment here is 0, but it's in the real beam moment 0, but in the conjugate beam there should not be internal hinge there. The internal hinge changed to some another thing that's called as internal roller. So these three things we need to get. So firstly we can say what's the bending moment diagram for this. For that you need to get the reactions. Let's analyze this part. Say here the reaction is D upwards and a moment of 30. So we can say summation of moments about this point C. So we can say if it is clockwise, that means it has to be downwards. Shear force of 30 by 15. We can get reaction of 2. You can calculate by yourselves. That's a reaction of 2. That means the reaction here it has to be reaction of 2 also. So reaction here is 2. Same reaction will get transfer to the to this segment, that's reaction 2 here. तो यहाँ पे भी आपका load 8 है. That means you can get the bending moment diagram. Can you get the bending moment diagram? I think so. So let's make the bending moment diagram. So here the value is 224 are 224 are 224 are means 48 plus 8 12s are 48 plus 8 12s are that's 144. Yeah, there's the effect of this one. So thing is that 2 into 12 Yeah, the reaction is upwards actually. We got the shear force here, it was downwards here, and same in this part it would be upwards too. So you calculate that 8 into 12 minus 2 into 24. The value is 48 negative. That means 48 downwards, 48 by EI. Then after that, up to this point, you need to get what's the value of that bending moment diagram at this point. So before that, you need to get the reaction also at that location, at location point A. For that, you need to get the shear force diagram. Say this was 2 and it was 8. That means shear force here would be upwards 6. So here the shear force is 6 upwards. So you can say 6 into 12. 6 into 12. You can do it side calculation. That's 6 into 12. That's 72. 72 minus 48. That is 24. 24. That means here the value would be bending moment diagram by EI. We can write that's 24 by EI. So you join by a straight line. Then after that, we know that at the internal hinge location there is 0 moment. So we can join the 2 points. That means at the internal hinge there is 0 moment. Then after that, it would be a linear variation such that at the final location you are applying a clockwise moment of 30. That means there would be a sudden rise of 30 kilonewton upwards. Let's say this is 30. There would be sudden rise of 30 upwards. So this is point C. This is point C. Moment here is 0, and we need to get this value, and this value is 30 by EI, because you are applying a clockwise moment of 30 here. That means there should be a sudden rise of 30 here. That means the line here should be 30. Then after that you join the 2 by straight line, because loads are only concentrated loads. Concentrated loads are only there. That means your bending moment diagram is a linear variation of that X. So we can say we got the bending moment diagram. Now we have to change the supports. We write the changing the supports. We write changing the supports condition. We have to change the supports. See, at the point where support is there, you have to make it as a free support. So there is no support actually. So it's okay. Then after that you have internal hinge here. इसको चेंज करने के लिए आपको इंटरनल रोलर यूज करना पड़ेगा. एंड यहाँ पे इंटरनल हिंज है, तो यहाँ पे आपका हिंज सपोर्ट है, तो आप हिंज सपोर्ट ही मान के चलो. एंड द लोडिंग इज what would be the loading? What would be the loading? See, this is negative, positive, and negative. That means in this part loading would be upwards, downwards. Loading would be downwards. In this part loading is upwards, and in this part loading is downwards. So we need to get the value of reaction at A and reaction C and reaction D. We need to get reaction C plus reaction D. That is difference of the total areas. We can say area net of loading, a net area of the loading diagram. Okay, understand? So the question is, get the theta CA. That means get the shear force just to the left of C. So we can write shear force just to the left of C, that we have to calculate. That is the summation of these forces. That's summation of this area, net area जो आपका यहाँ पे आएगा. That's one part is upwards, next part is downwards. Net would be some difference of the two. So we can say, can you calculate that value of x? Let's say this is value of x. We can write 48 plus x divided by x equals to 24 by length of 12. Total length यहाँ पे 12 था, 12 or 12 minus x. So your x value comes out to be 8 meter. If it is 8 meter, can you calculate what is this total length up to the point C? That means it's 4 plus 12, that's 16. 16 मीटर है आपका यहाँ पे. Yeah, this. So we know the p coordinates. This is 48 and this is 24. We can get the net value of the area. We can write. So we can write. Let's say the shear force here is V. Just to the left of C, we can say shear force just to the left of C. That's upwards. We can write upwards plus. Then we have 1 by 2, 24 by EI into length of 16 meter. Yeah. Then we write minus 1 by 2, 48 by EI into length of 8 meter equals to 0. The shear force just to the left of C, that is 0. That means theta in the span CA, that is 0 for the real beam. So that means shear force, that means theta here developed would be 0 in this part. Let's say theta developed here would be somewhat this way, and in this part there's some theta. Let's say calculate that also. So let's calculate now theta in the CD part. Let's calculate the theta in the part CD. Let's say this is the part CD, and you cut just before C. Let's say here the shear force is just to the right of C, that we need to calculate. And we have downward loading of uniformly varying load of 30 by EI in the length 15 मीटर में आपका ये वैरी हो रहा है, 15 मीटर में आपका वैरी हो रहा है ट्रायंगल. तो इसका एरिया और reaction is also there, some reaction D is also there, net reaction D. So that you need to calculate first. That is the main concern here. So shear force you need to calculate. So for that you say इसका centroid यहाँ पे है, इसका centroid यहाँ पे है, और इसका centroid यहाँ पे है. You can say, you can calculate that if you take summation of moments about C equals to 0, you can get reaction D. So directly you can say, if you write summation of moments at C equals to 0, you can get reaction D. So we can write reaction D is upwards. Let's assume reaction D is upwards. We don't know reaction D where its direction is. We can say it's upwards. We can write D into 15 anti-clockwise. Then we have, because of this is positive 1 by 2 into length of 15 and intensity of 30 by EI, and it is clockwise. Then we write इसका effect, it's upward loading, that means it's also clockwise about C. That's 1 by 2, 24 by EI. But we have two triangles because इसका अलग centroid है, इसका अलग centroid है. So we write 1 by 2, 24 by EI. The length of this one is 12 meter. So we write 12, and the centroid is acting at 2 by 3rd of 12. Similarly, we forgot the centroid of this one. The centroid is actually 15 by 2 in 2 by 3 of 15. So you have to multiply here 2 by 3 of 15 also multiply it. 2 by 3 of 15, that's 10 meter. Similarly, you have this triangle and you have this triangle also. Now you calculate this one also. So you write that 1 by 2, 24 by EI. Then you have length of, ये length कितना है? ये x was 8 meter, that means this length is 4 meter. So write 4 meter into centroid. Centroidal distance is equals to 12 plus 4 by 3. 12 plus 4 by 3. And similarly, you have one more triangle that's loading is downwards. So it is anti-clockwise about point C. So we're at minus 1 by 2. We're at minus 1 by 2. So we're at minus 1 by 2. Area of the triangle, that is 48. 48 by EI into length of 8 meter. And the centroid is acting at a centroid conclusion is at, say, from this point to this point, that is यहाँ तक था 16 meter. After that 16 plus 2 by 3rd of 8, then equals to 0. That means you can get the reaction D. That reaction D equals to some value. So the reaction D comes out to be equals to, the reaction D is equals to minus 3.6 by EI. So you got the reaction T minus 3.6 by EI, minus 3.6 by EI. So you got the reaction minus 3.6 by EI, and that's upwards, that's downwards. That means the direction you assume it's actually downwards. So here the reaction is 3.6 by EI. So you write the summation of shear. So we can write VGRC plus this is downward load, so 1/2. So we can write upward positive and downward negative. We can write 1/2, 15 into 30 by EI minus 3.6 by EI. So this is 450 by 2 plus 3.6. So we got the shear force that equals to 228.6 by EI. That's negative. That's positive. That means the direction assumed is correct. So your shear force, that means your theta in the span CD in the real beam equals to 228.6 by EI. So that means there is some theta developed in this span. For this part there was theta 0, but in this part there is some theta equals to 228.6 by EI. Now we need to get the third part, that's delta C. So delta C can be calculated by the moment at C in the conjugate beam. So we need to get the moment at C in the conjugate beam. So we have calculated the shear force at the point C. We need to calculate now moment C. Can we calculate that moment C? So we have already calculated one part of that we know. Areas we know. We can say, let's say this is MC clockwise positive, and because of this is also clockwise, we can write this one also clockwise, plus 1/2, 15 into 30 into 30 by EI, acting at length of the centroid. कहाँ पे acting इसका कर रहा है? That's 2/3 of 15. 2/3 of 15. Then there is also this clockwise moment of 3.6. So we can write 3.6 by EI into length of 15 meter. That equals to 0. So moment C is negative times some value 2304 by EI. That means deflection at point C, it is downwards 2304 by EI. So deflection of 2304 downwards at point C. So the conclusions are that the sign conventions that we have used in the conjugate beam method, you have to write those which we followed. That if the moment in the conjugate beam, you got moment at any particular location I in the conjugate beam as positive, that means the deflection at that particular location in the real beam, that's upwards. But usually आपका moment negative आएगा, that means deflection is downwards, because usually loads are downwards, so deflection would be downwards. You prefer this one, that if the moment in the conjugate beam at particular location I is negative, that means deflection at that particular location is downwards. Yeah. So we got this one also. Do you have one more problem? I think this is the end of this entire section of that conjugate beam method. We are done with all those deflection methods. सारे deflection methods हमने solve किए हैं. तो deflection of beam is over. So we are now focusing on next topic. Let's see which topic to be selected. So we are over. So conclusion is that deflection of beams, say we had deflection of beams. So first method was your double integration method. The equation was EI d2y by dx2. Then you double integrate it to get the value of deflection. If you once integrate it, you can get the value of, once you integrate it, you get the value of theta, and when you double integrate it, you get the value of deflection. And similarly, after that, Macaulay was advancement over a double integration. It included all those spans. It wrote all those, it wrote the moment equation for all those spans. Then the sign, we applied that oblique sign. It said whether the terms are valid or not. Then after that, we had, after Macaulay, we used the superposition method. Then once you know there is standard results, you can directly calculate the deflection profiles quickly. You can calculate the delta very quickly. This is a very quick process, quick method. Once you know the deflection profile already, then you can get the delta and theta. After that, superposition, we use it as energy principles, that external work done equals to internal strain energy stored. Based on that, we had one method that we studied, Castigliano's theorem. It says that if you want to get the delta at any location I, you integrate it with respect to you integrate the strain energy, total strain energy of the structure with respect to that load at a particular location I. If the load was not there, then you apply a pseudo load there, pseudo load. Then after that, you set the pseudo load in the u equation equals to 0. Finally, if you want to get theta I, you say dou u by dou m, the load, the moment you applied at location I. Then after that, you have one more, that was moment area method, and you have conjugate beam method. See, the rest method is used that moment equation, mx equation, moment at any x. You cut the section, get the moment equation at any x. But in the moment area method and in the conjugate beam method, you calculated that, get the bending moment diagram. So get the bending moment diagram, then you divide by EI. Similarly, in this case also, get the M, then you divide by EI. So M by EI diagram, you worked on M by EI diagram. Then you have here you have two theorems. In this one, you also have two theorems. First one was that if you want to get the theta at B with respect to the tangent drawn from A, that would be area under the curve between the 2 points. Area of M by EI diagram between the 2 points. Similarly, if you want to get the deflection of B with respect to tangent drawn from A, that's area, that is moment of area about the point B, where you want to find the deflection, delta B, that's centroid about B, centroidal distance about B, into area between AB. After that, you have theorem. After that, you have that conjugate beam method. Conjugate beam method says, if you want to get the theta at any location I in the real beam, you do one thing, you make conjugate beam, get the shear force at that location I in the conjugate beam. That's called a surgical strike. Surgical. And similarly, if you want to get the delta at any location I in the real beam, do one thing, make conjugate beam by changing the supports, get the moment at any that bending moment at that location I, and you can get the deflection at that location I. But one thing is that, see, if in the next one is that concept of internal hinge. See, we have solved problems on internal hinge using moment area method and conjugate beam method, but we have not solved, and also we use superposition also. So in the Castigliano's theorem or in the Macaulay's method, but we have not used internal hinge problem, any internal hinge problem, because of the internal hinge, there's discontinuity in the slope, or continuity in the curve. Say, because of this, there was some theta here 0, but in this part there is some theta. So here the theta was 0, but here in this part theta was not 0 at the particular location C, as we have solved the previous problem. So we cannot solve this one using that EI d2y by dx2, because y is changing that at a particular instant dx. So we can say, and similarly in the Castigliano's theorem, you cannot use that change of I. if the prismatic bar, if there is a prismatic bar, if there was prismatic bar, you can solve only if the beam is prismatic. But your moment area method says no worries about that. Moment area method says no worries about that. I can handle also that EI changes. So it can handle EI changes. I think this is sufficient. End of that those deflection of beams concept. So thanks for watching this series of deflection of beams. Hope you understood the concepts and the problems we solved. Thank you.